In this section of projectile motion, we are going to look at projectiles that are launched at an angle. So recall that projectile motion is always analyzed as horizontal and vertical motion separately. And also recall that horizontally there is no acceleration because there is no force acting on it in the horizontal direction. So it is moving at a constant velocity in the horizontal direction. Vertically though, gravity acts on it and therefore it is in free fall, accelerating at negative 9.8 meters per second squared. So if you look at a projectile that is launched at an angle, say you are on the ground and you kick a ball. So what trajectory does it take as it falls to the ground? So let's fire something and see what happens. So you can see as this projectile is going to take a parabolic path as it falls to the ground. So why is it taking a parabolic path like this? So this projectile is moving in two dimensions. Horizontally, what it's doing is it's moving at the same speed all the time. So that means horizontally, this is what it's doing. It's here at 0 seconds, 1 second it travels a certain distance, same distance the next second, same distance the next second, same distance the next second. So it's just going at the same speed all the time. Vertically though, it's in free fall. So it starts going up from here. But as it goes up, it is going against gravity, so it slows down, so then travels a smaller distance and then a little bit lesser until finally it stops at the very top and then it comes back again. You know, even though it comes back along the same vertical line, just to distinguish it for you, I'm going to redraw it like this. So it goes up and comes down as in free fall. So if you combine these two motion, while it is going up and down, it is also being pushed horizontally at the same speed, you get a parabola like this. So therefore we have to analyze horizontal and vertical motion separately. So let's look at what we have done here. I have launched the projectile at 16 meters per second at an angle of 57 degrees. So we're going to take those numbers from there, 16 meters per second at 57 degrees. And we want to analyze how much time the projectile stays in the air and how far does it go and so on and so forth. So T represents the time of flight or the total time it stays in the air. The horizontal distance, delta x, we know this horizontal displacement is also referred to as the range of the projectile. So the first thing, even before I start doing horizontal and vertical motion, I need to first know what is the starting velocity in the horizontal direction and what is the vertical velocity in the horizontal direction. So I'm going to take this velocity and divide this into two parts like this. Notice how this triangle is so small and cannot be seen, so I'm going to just enlarge it here. So if this is my initial velocity, I'm going to divide this into horizontal and vertical. Okay, and this angle is 57. How do we do that? So call this Vx and call this Vy. We know that we can use the trig ratios. So let's say cosine cosine 57 so cosine 57 is adjacent over hypotenuse, so bx over 16, and multiplying both sides by 16, we know that bx will be 16 cosine 57, and make sure your calculator is in the degree mode when you do these calculations. So 16 cosine 57 is 8.71 meters per second. This is the horizontal speed. Finding the vertical speed, we want to do sine 57 because it involves the opposite side, which is what we are looking for, Vy over 16. So Vy would be 16 sine 57, which would be 13.4 meters per second. Notice because the angle is more than 45, your vertical component is more than the horizontal component. So that means this is how fast the projectile is moving horizontally. This is how fast it is moving vertically at the starting point. So now let's go to our horizontal and vertical columns and write this down. We want to make sure that we write this down so that we don't do this mistake of mixing up these velocities. And our Vy would be 13.4 meters per second. So now we want to solve for the time. So if I look at the vertical, let's imagine that our vertical motion, you want to just look at the vertical motion. Vertically what it does is it starts at a speed of 13.4 meters per second. But we know as it goes up, it slows down until at the topmost point, our velocity becomes 0. And then again, while coming back, it increases back to negative 13.4 because it's in the downward direction, right? So I can make use of this knowledge in order to solve for the time. So my Vi, the initial velocity, is 13.4. My acceleration is negative 9.8 meters per second squared. And I'm going to set my final as 0. That means I'm only going to look at this part of the projectile. And since I have 3 variables, this allows me to solve for the 4th variable, time. So Vf equals Vi plus A delta t. So 0 equals 13.4 minus 9.8 delta t. So that gives me delta t as, so rearrange, solve for delta t. You will get 1.37 seconds rounded off. But remember, this is not the time that I'm looking for. This is only time to go to the top, and I want to solve for the total time. So that means I need to double this in order to get the total time it stays in air. So total time should be 2 times 1.37, and that should be 2.74 seconds. So this is how much time it stays in air. Now that I know this, I can easily solve for the range, because we do know that horizontally it is traveling at the same speed. There is no acceleration. So I can simply say distance equals speed times time. Therefore, it is going to be 8.71, which is my horizontal speed, times the time, which is 2. Keeps doing this. Which will be 23.9 meters. So this is how far the projectile traveled horizontally before it landed on the ground. Let's go to our simulation and check these answers. So I'm going to take this tool to put it here to see if we measured this correctly. So it's about 2.74 and 23.8, which is more or less what we had there. So sometimes we are also interested in solving for the height. How high did the projectile go before it fell to the ground? So if you want to solve for the maximum height, that's just a question of the vertical motion. So we just have to do it like a free fall problem. So I want to know how high it went. But I do know what is the starting velocity vertically, and I know the final velocity, and I also know this time. So therefore it becomes simply easy to just use this formula. Displacement is average velocity times time. Let's see if you know how to substitute correctly. So our starting velocity is, that is correct, we need to use the vertical velocity, so that is 13.4. Our final velocity at the top is, yes, vertically it is 0, divided by 2 times time. You are right, we have to use only the time taken to go to the top, which is only the half time, which is 1.37. So using this, we can calculate the maximum height to be about roughly 9.2 meters. So if you want to choose to call it as maximum height or delta y, either one works fine. So that is going to be 9.2 meters. Okay. A couple other things with the angle projectile is you want to be able to understand what happens as you manipulate the angle. Notice that if I increase the angle, fire again, you can see that even though it went higher and took a longer time, 3.08 seconds compared to 2.74, the range is kind of shortened. So when you increase the angle, you will notice that the vertical component keeps increasing. As a result, it's going to travel higher and take a longer time. But since the horizontal component decreases, it's not moving as fast horizontally, so therefore the range decreases. But guess what? There is one angle at which you will get the maximum possible range, and that is 45 degrees, because you get the advantage of maximizing the horizontal as well as the vertical component. So this is the one where it's going to go the furthest. So range is maximum at 45, but the time and the height is going to depend on the vertical components. So the higher the angle, the greater the time in air and greater the height. So you want to come back to this simulation and do some manipulation yourself. To summarize, the first thing that you would do in these problems is to split the speed or the velocity into two components, horizontal and vertical. Vertical is like a free fall problem. We can take advantage of the fact that the vertical velocity at the topmost point is 0, and we know that. So you can solve for the time to go to the top, double it to get the total time, put that back in the horizontal equation, and you can solve for the range. Okay, until next time.